This is the warm-up moment because I've got a minute before we start. So I'm going to ask these questions before I actually start. How many admins are in the room? I was hoping to get a few. Good. All right. Excellent. Developers? Architects? Marketing people? Anybody? Okay. Yeah. Excellent. All right. Very cool. Just thought I'd get a feel for that. I've got 30 more seconds. Any other questions I want to ask you and get out of the way?
Where'd you get that amazing t-shirt?
I got that at Shirt Force.
There we go.
All right. Just to get a sense, AI experts in the room? Oh, thank God. So how many people have done some machine learning work of some sort in this room? A few people. Okay. And how many people are literally walking into the room with no concept of actually what an AI model is? Okay, how many people have some concept and they're curious to see what Peter's going to say? Okay, all right. Well, this will be a fun talk. I think it's time to get going, yeah? Is that good from the text below, out in the back? Good for my timer in the front? Excellent, all right. So my name is Peter Chittum. This is Making Sense of AI Models. I am not an AI expert, just to say that ahead of time, but I am trying to learn. My proper job is as a developer relations advisor. I worked in developer relations for 10 years at Salesforce, 12 years total. I've always been, for a long, long time, I've been doing developer enablement, and now I'm doing it freelance for a couple of clients in the Salesforce ecosystem, one client not in the Salesforce ecosystem. So let's jump on in. Here's the agenda at a high level. I'm going to try and answer the question very briefly, what's an AI model? I'll walk through an example of one using a very basic AI algorithm called linear regression. And then I want to talk about some common machine learning models outside of LLMs and generative AI. We'll then go into generative AI, and then I just want a short word at the end and talk about sort of generally about model selection, although I'll kind of give some tips along those lines as I go. I'm going to use the terms AI and machine learning interchangeably. There are some people who are in AI who only believe that symbolic AI is AI. Sorry, we'll just have to disagree. We can talk about it afterwards. But I just wanted to make sure that that was clear. So this is the question. What is an AI model? This really drove me to want to learn more about machine learning because there was all this talk about there's this model here and that model here, and this model has this many parameters or does this many tokens or has this context window. But I couldn't get a short explanation of an AI model. And I'll tell you, I can barely fit into 25 minutes, so now I sort of know why. But briefly, you could say an AI model is something that, some kind of technology that contains a set of inputs, and we call those features. It has an algorithm of some sort, and then it has a set of learned parameters, learned data, which are called parameters, and then finally, it's going to produce a prediction. So if you take all of those things together, thank you. I hope you enjoyed my talk. But let's actually look at this in a little bit more detail and go through two different phases of machine learning models. One is inference, which is where models make the prediction, and then the other is training, which is the learning part of machine learning. So a model, as we said, is an algorithm, right? So it's some code that gets repeated, right? And then these learned data that are called parameters. And I'll get back to kind of what that exactly means. We also have some input data. And so the input data are going to be the thing that you provide the model. And now with LLMs, of course, that's text. But previously, it was typically some kind of numbers or classified values or that sort of thing. And then the model makes a prediction. So this is what inference is and what it means. And this is pretty true across all machine learning models. But how does it learn? That's the thing that I wanted to know, really. What does it mean for a machine to learn? So let's talk a little bit about that. Now, in the beginning of the learning process for machine learning, I have features, right? This is the data that I know already today. And then I have some parameters, but we just said that the learning part is about learning the parameters. So what are these parameters at the beginning? Well, that can kind of vary. Sometimes it's called initializing parameters is when you're going to start out the process. And sometimes you initialize them to 0. Sometimes you randomly initialize. Sometimes you actually use the features to initialize your parameters. It just kind of depends on the machine learning architecture you're working with. So we're going to take those two big chunks of numbers, stick them in the algorithm, and we're going to make a prediction. Now, this is going to be a rubbish prediction to begin with because we don't have any data in the parameters that's useful. And that's the point. We're then going to take a look at what that output is and put it into something that's called a cost function. And this compares what that output was with something that we know or something that we hope to get from the model. The difference then is used to slightly adjust the parameters and then repeat the process. And that is what that's how machine learning actually takes place. So that's the training process for a model. The interesting thing about this is, more narrow AI models, you might go through this thousands of iterations. For the large language models, the number of iterations is, however many iterations you can go through over sometimes months of training. So like how many iterations really varies greatly on the model architecture. I want to go through this in a bit more detail as well, using an actual use case as opposed to the sort of general hand-wavy version. And we're going to take a pretty classic, when people are learning machine learning, there's a classic use case of house prices. There's a data set that gets used a lot for this. And of course, the thing that we might want to predict would be a house price. And we might base that off of all the different data that we have about houses. We're going to use an algorithm called linear regression. Linear regression is basically the same statistical model that you would have used in your statistics class, but automated, obviously. That's the whole point behind it. And the whole point of linear regression is put some numbers in and get a number out. That's really what you're trying to do. So it fits the predict a house price model pretty well. Now we're going to really simplify this. Instead of having a bunch of parameters about the house, we're going to start with just one single one so that we can understand the concepts here. And that's the area of the house. That's going to be our input feature. And what we want to output is a house price. And if we take our x-axis and say that is our square footage in area or square meters, actually it should say square footage based on the numbers I have. And then if we say our y-axis is the output, then we can have a nice, neat plot of all those different data points in a two-dimensional graph. And that number 2 dimension is important for kind of how we can learn about this process. What we're looking for is what we would call best fit. And this is a pretty straightforward set of data, so you can sort of imagine where that line would go. That would be pretty close to the middle of all those data points. And then there's 2 important numbers that we can know about this line. One is where does it cross the y-axis, and the other is what is the slope. And those 2 things are called bias and weight. And most machine learning models have some form of bias and weight in the way that they do their work. So even in this very basic, simple example, we could project this into other ways of doing machine learning. And that's also why most people, when they start learning this, they start with this example. We're then going to train this, right? So as we said, we're going to initialize the parameters to some predetermined values, some arbitrary value. And we go about the process of then measuring that once we've output, based on that, initialized weight and bias value. We measure the difference between that plotted line and all the data points, and we're going to kind of average that and come up with a number, and that's called sometimes it's called the error or the cost. And the term error function or cost function, those are interchangeable for the most part. And I should say most models call it this. There are some other models that call it something slightly different. So there we go. So we have our first measurement. And as we said, we repeat that process. So over time, over the learning process, we're going to be adjusting the parameters, adjusting that weight and that bias so that eventually that line finds itself into that nice, happy middle point of all of our points. And that's the place where we can say that the model has converged. And converged means that I can then take this information and do inference with it and probably get a decent output. So if I get a new house now, after all of my training, and I know that that's 3,500 square feet, I might know that that's an $850,000 house, which actually a year after I first probably built this slide, that's starting to underestimate it a little bit. So that's the process of going from we know nothing except we have some data to start with. We want to then take this algorithm and teach it to use that data. But the important point is normally you wouldn't just have one parameter because one parameter is not going to make for a very accurate prediction. The problem is, you can get to 2 parameters and have a 3-dimensional graph representation, but once you hit 4, our brains don't really process that. And so that's kind of why you start with a very simple example to teach these sorts of things. It's important to say also that there is no finish line for your model. Take an example of housing prices again. This changes over time. So, new data is coming in all the time. Old data ages out. For models that are self-learning, there's something called model drift, where your original objective your model can move away from its original objective just because of the organic data that has come into it. We've seen interesting things like that happen in chatbots and social media in recent years. And I wanted to take a moment, in and amongst this presentation to have some touch points back to Salesforce. So why is this relevant to me? Well, you're going to need to, if you're going to have an AI project, you may need to select what kind of model. And that was another reason why I wanted to start giving this talk in Salesforce spaces, is so that people could begin to understand what the trade-offs are for these. In fact, linear regression is this type of model in Model Builder. They call it a general linear model, but it is linear regression. It's the same type of model. So actually, one of the nice things is you don't need to know all the machine learning stuff to get a linear regression model working in Salesforce. You just need Model Builder, which means you need Data Cloud. So bear that in mind. And the thing that came to me, and I think, I'm sure I'm not the only person who's come to this conclusion, is machine learning is really about using data to find connections through math or maths, depending on which continent you're from. So let's go through a little harbor tour of a few other machine learning model types. Normally, I spend a bit more time on this section, but I sort of had to narrow this down so I could fit a bit more on the LLM side. Broadly, apart from generative AI, there are 3 broad categories of machine learning: supervised, unsupervised, and reinforcement learning. Supervised would be I have some data and I know the outputs that I want from that to do the training. And I'm going to enter put those into a model that's going to learn and then, be able to produce outputs, to be able to do inference accurately. Unsupervised learning is I have a whole bunch of data. I'm going to use a model that goes and finds the patterns in that data. And there's some really cool models along those lines. And then the last one is reinforcement learning, which before the current LLM craze that we're now finding ourselves in was kind of the super sexy machine learning that was going on. But machine learning is kind of the thing driving a lot of things around robotics and autonomous driving. There's some things around like assistive medicine and that sort of thing. Reinforcement learning is where you put an AI agent into some kind of problem space or environment, and then it just basically flaps around in that environment until it learns the right patterns to follow. It's kind of a good way to put it. I'm not going to read through this entire list, but I put this up here to just reference where some of the things you may have heard of fit into these different types of or categories of machine learning. Classification is a pretty standard problem, and there is a very simple classification algorithm called logistic regression. In practice, this doesn't get used a lot, partially because linear regression can also be used as classification as well. And so in the end, this isn't a model type that gets used very frequently. But what can happen is you might use both linear regression and logistic regression to stack a bunch of those nodes together into what's called a neural network. And that's basically what a neural network is: a whole bunch of smaller algorithms who've gone through a training process together to be able to come up with some intuitive conclusion about some kind of problem or data. Feed-forward neural network is one term for this, and that would be sort of a single-direction neural network. Recurrent neural networks are where you have a neural network that constantly feeds the new data back into itself. So there's different flavors of this, but all of those are still neural networks. Decision tree is not one that gets talked about a lot, but interestingly, the decision tree algorithm is probably one of the more interesting and important algorithms for business. And a big reason for that is that one of the things decision tree algorithms have going for them is that their output is very interpretable. And that means that when you get a particular classification value, there's a high probability that you can understand why it made that decision. And you can understand that in a sector where you might have a lot of regulation or where you might have a lot of compliance, knowing why you got a machine learning value could be very, very important. It's one of the fundamental problems of LLMs that people are trying to solve right now. And so something like a decision tree, you can actually know pretty much what was the thing that got you to, well, this is this type of widget. And interestingly, Model Builder chose two different forms of decision trees to make available to you if you're going to go and do some classification. Now, these two types of models are both decision trees, but they each kind of have their own specialization. Thank you. The first one, GBM or gradient boosting machine, is good for smaller data sets. It is more interpretable. If you have a very large data set, though, it can be very slow, and that's where the XGBoost type of model might come in handy. Unsupervised learning algorithms are kind of the coolest ones out there, like clustering algorithms and anomaly detection. Recommenders, everybody's probably seen one of those because every e-commerce site has one. Reinforcement learning, I wish I could talk about it. I don't have time, but check out this. There's a great YouTube video about somebody doing reinforcement learning with Donkey Kong. It's the Code Bullet YouTube channel. And that brings us to generative AI, which is what kind of everybody's interested in today. I like this quote. I think it's true over and over again in technology, and we're living through one of those moments right now. Even with as much as I've tried to learn about machine learning, it can still feel a bit magical when an LLM surprises you. The transformer is the architecture that kicked off this whole revolution that we're in the midst of, and it came out of a paper in 2017 called Attention is All You Need. It's called that because it took a single-minded focus on one particular architecture called attention. They call it the attention mechanism. It had been used in language processing before, but they decided we're just going to do a model where that's the thing that we use. We focus everything on that. And what happened was that it had these certain advantages over the previous architectures. So one big thing is it could do parallel processing of the input. And that's recurrent neural networks are doing one iteration at a time for each word. So that was very problematic from a performance standpoint where you have a large body of text. Also, that gave better scale. There's also less data loss for that. And then what they found is it generalized very well. So even the original transformer, would, it was intended to be a translation algorithm. But what they found is they could also do text classification very well with it without even training it to do that. So that was kind of a big discovery. And then as people experimented with this, they started dumping more and more data in. So they would do bigger models, more parameters, more tokens, more data, more vocabulary, if you will. And what they found is that they could get these new behaviors that they didn't actually train for. Those were called emergent behaviors, if you ever see that referenced. So that's where those attentions are in the diagram. I really struggled with what angle to come at transformers to have 10 minutes to talk about them. So I just want to talk about a few things about them that to me were a bit surprising as I dug into it. So if I have an input, right, I have my model, the actual transformer model, I went a bit too far there, is a little different because I have not just an algorithm, but the transformer is really more like a composite of algorithms. I also have lots more parameters, the smallest models. In fact, Salesforce just announced an agent model recently, just like a couple weeks ago, that's going to be a 1 billion parameter model that's going to go on your device. Now, the biggest ones like GPT-4, I think was in the 1.2 or 1.3 trillions of parameters. So that gives you a sense of the scale and why they take months to actually train. LLMs also will have a vocabulary. I should say any transformer model is going to have, you could call it a vocabulary, and something called embeddings, which are the meanings of the words of that vocabulary. And so we're inputting text, right? That's what we call a prompt, which is a really well-known term. And the output is going to be called a completion. So I get some more text out. And just to make it clear, right, when I talk about the vocabulary, that's that word tokens that you've heard probably a lot when you hear LLMs. And this is one of the things that I think is really important to understand, because how do you take text and do math on text? And that's really where tokens do come in. Because tokens, actually the language model itself never sees the words. What they're going to see is an identifier for that word or for that token. That token then is going to have something called an embedding vector, which basically establishes its meaning in the broader vocabulary. And I have an animation of this, but instead I'm just going to take it, do this slide here. There we go. All right. So this is actually taken from the embedding projector on TensorFlow. And this is obviously a 3D representation. But in reality, this particular vector is a vector of something like 768 dimensions. So it really blows your mind to try and how does the model think of the meaning of this thing? So we take our embeddings, and those are little blobs on top. The transformer will also have an encoding of the order of the words. There's also going to be an encoding that has all the relationships between all the words in your input text. And of course, all of those are numbers, and that's going to go through many layers of transformers. At that point, there's going to be an output. And at the end of that, for every single token, there's going to be a score. And there's going to be the most likely token all the way to the least likely token. And this is where we actually have a lot more control. Now, who's heard of temperature before? Yeah, and so this is one way of getting more variance. But you can also actually completely turn off the variance entirely, and that's called greedy selection. Or you can pick a certain maximum number of tokens, either by number or by probability, and that's what top K and top P are for. All right, wow, here. So those are just a few of the things that, as I pulled apart what a transformer is, that to me, I found interesting. And so I just want to wrap up and say, when it comes to selecting your model, because I think many of us are going to need to learn how to do this as we go out and get into projects where somebody comes to you and says, we need some AI, and you need to ask the question, well, why? And that has always got to be the first question, because before anything, you need a use case. In fact, many use cases where somebody might want to solve that with AI might not even need it at all. Or maybe you can use a more narrow model, or maybe you actually could use an LLM. And apart from that, once you've established you do need it, of course, cost, time, and skills are all super, super key to this, how is that different from any other project that any of you have worked on, right? It's the same problems that you're trying to solve for. There are some unique things about AI models that are worth talking about, though. Cost right now is probably really hard to gauge, especially because for a long time, cost of training seemed like it was going to be the big expense. But now what's happening is with AI apps, you don't just do one round of inference, you actually make many, many calls to AI models. Has anyone used Copilot for Salesforce? Anyone watched it take like half a minute to generate its, right? Actually, Salesforce is, because of the Einstein trust layer, is making something like 5 or 6 different inference calls just to provide you that trust layer. So it's no wonder it takes a little while for it. And if you've played with some faster models, it doesn't feel so snappy when you're in Salesforce Copilot. But I think that's because they're trying to deliver the safe version of what we want. Time is always critical, and these days nobody's going to train their own LLMs. It's very unlikely anyway. Salesforce is obviously researching that all the time, and large software providers are researching these big foundational models. But much more likely, what you're going to do is take an existing model, You're going to fine tune it. You might use what's called RAG, or retrieval augmented generation, which is just basically better prompting. Or you might just use some prompt engineering for it and make that work as well. And then skills, I think, is worth talking about because, those of us who've been through the, up until about 2023, there was always a talk of a massive gap in Salesforce skills. And if you thought that was bad, you should look at what it is for machine learning professionals today. If you're in a place where you want to explore something new in the technology world, I would have to say this would be the time to take a look at machine learning. There's a lot of need for it. And one particular role that I've thought of for Salesforce people that I think a lot of people could start looking into, and that is something called the machine learning solutions architect. I don't know that I'll ever be a machine learning engineer. My maths are a bit sketchy for that. But I think that solution architect thing looks really intriguing because I can imagine the problems that I might need to solve. And if I can get to a point where I have an intuitive sense of how this AI stuff works, I could probably be of some value on a project. So that's pretty much it. I did want to say, Andre Van Kampen here is going to be doing a talk. I didn't talk anything about the data problem, and his talk is called Wake Up Call, Confronting Data Chaos Before You Fantasize About AI in Salesforce. So I want to pitch his talk because I think it'd be very complimentary. I've been all about the model. He's going to be all about the data. So go check that out. Where are you? King's Vault? Okay, so go check out Andre in King's Vault. I'm sorry I didn't leave time for questions. I hope it was valuable listening. If you do have questions, I'm around for the rest of today. I'd love to chat. Thank you very much.